Okay, so this video is a final exam review of Chapter 6, Rational Expressions and Functions. So first off, let's go back to the definition of a rational function. It'll have this form here. Notice we got f of x equals p of x over q of x. Got a function over a function here. Notice something very important. Q of x, the function in the denominator, cannot equal 0. Because if we have the q of x, the function in the denominator, equal to 0, we would have division by 0, which is undefined. So for that reason, the domain of a rational function includes all real numbers except those that make q of x, that is, the denominator, equal to 0. So we exclude values that make the denominator equal to 0. Moving on to the next. So I'm going to go a little bit more into detail about what happens with these things around excluded values. It's kind of getting into your next class, but we'll go ahead and include it here just to further emphasize the point. So the domain of this rational function, f of x equals 2 over x minus 5, what's in red here, the denominator function, cannot equal 0. And if we were to set the denominator equal to 0 and solve, we would see that 5 makes the denominator 0, as it says here. So the domain will include all real numbers except for 5, because 5 would make the denominator equal to 0. Now, this is not the exact figure in the book, but notice at this point we got 1, 2, 3, 4, 5. At x equals 5, remember that is the equation for a vertical line, we have the graph of this function here doing something kind of strange. Notice that in the denominator it gets infinitely small, and then, to the left of the x equals 5, it gets infinitely small, and then to the right of x equals 5, it gets infinitely large. We call this, new word here, an asymptote. But what you really want to take away from this is that the denominator, whatever makes the denominator 0, is excluded from the domain. Notice that it will never cross or never equal, the x will never equal 5 because it's excluded from the domain. So here we're going to say finding domains of rational functions. It says give the domain of each rational function. F of x equals 3 over 7x minus 14. And it says the values of x that make the denominator 0 must be excluded from the domain. To find these values, set the denominator equal to 0 and solve the resulting equation. So what we do is we set the denominator, which is 7x minus 14, equal to 0. We add 14, divide by 7, we get x equals 2. So as it says here, the number 2 cannot be used as a replacement for x. The domain of x will be all real numbers except for 2. Now remember, we wrote the domain in two types of notation, one being set builder, the other being interval notation. So in set builder, remember, we use the set brackets, and it's written as the set of all x's, where x is a real number, comma, and then we identify the excluded value, here x not equal to 2. That's set builder notation, okay? Then there's interval notation, which is written as, again, we're indicating all real numbers except for 2. So we identify as in negative infinity to 2, union 2 to infinity. So a couple of things to note. Set builder notation identifies the value that the domain cannot include, x not equal to 2, and interval notation indicates the numbers that are included. So there's a couple ways to look at these two things, but what you really want to take away from this is There's set builder notation, and it is represented in this way. Then there's interval notation, which is represented in this way. There's two different notations for identifying domains. All right, so another thing I want to point out from this chapter is that these rational expressions can be written in lowest terms. So what you do when you're doing to get these written into lowest terms, what you do is first factor the polynomial. So in A, notice we've taken this and we factored both the numerator and the denominator. Now notice there's something in common between the numerator and the denominator, the y minus 1. So the y minus 1 cancels, and there we've written this now in lowest terms. Now B is there. It's sort of a trick question. Notice the B, we think that we might be able to factor the binomial in the denominator, but actually it's a sum of squares, not a difference of squares. Remember, there is no formula for sum of squares to factor a binomial that is the sum of squares, only a difference of squares. So this one is already in lowest terms. Now, C happens to be a sum of cubes here. So we'll use the sum of cubes formula here to factor this. And once we've used the sum of cubes formula to factor it, we'll notice that 1 plus p is common between the numerator and the denominator. So those will cancel out. And now we've written this rational expression in lowest terms. So what you want to take away from this is that to get it written in lowest terms, first you factor it, and then you cancel out the common factors, and then you've written it in lowest terms. So we're going to look at this problem that'll be on the final exam. It says, give the domain of the following rational function using set builder notation and interval notation. So we've got to represent the domain in set builder notation form and interval notation form, looking at the function f of z equals z over z minus 4. Remember, we exclude values that make the denominator 0. So what we would do would set the denominator equal to 0. Z minus 4 equals 0. We solve that for z. We get z equals 4. 4 is the excluded value. Now A, remember, it wants it in set builder notation, so it says here the domain of the given function is the set of all z's, where z is a real number. Z not equal to, that is where we put the excluded value on this problem. And then B, remember, is asking for an interval notation. So the way that we write it in interval notation is negative infinity to the excluded value, union, excluded value to infinity. So we put the excluded value here in this notation. What this is demonstrating is all values except for 4. So again, remember the set builder notation identifies what the excluded value is, while interval notation identifies what values are included in the domain, and you put your excluded value right here. So, rational expressions. Remember, when we have a common factor, we cancel those out to write the rational expression in lowest terms, which is what this question is asking us to do. Don't miss this question. This is really easy. You just got to apply what we know about rational expressions. What do you notice in common here? Notice we have z minus 1 in common between the numerator and the denominator. So what we do is cancel out the common terms here. And now we've written this in lowest terms, and that's all we've got to do to that one there. So that's an easy problem. Don't miss that one on the final exam. Now this one is still an easy problem to do, but just remember the rules. First, we factor the numerator and the denominator, because we're eventually going to try to get some terms to cancel out. So the numerator, we can take out a greatest common factor, and in the denominator, it's a a difference of two squares. So first we're going to factor the numerator and denominator. So in the numerator, I factor out the greatest common factor of 4. That leaves me with t minus 2. Then, as I said, the denominator is a difference of two squares, which we apply this formula right here, remember. So that means t minus 2, t plus 2. Now we have a common factor here, a common factor of t minus 2. So now we cancel out our common terms, and we're left with the rational expression written in lowest terms as 4 over t plus 2.